Morning, everyone. So in preparation for the final, I'm going to overview the 5 chapters that we covered in Chem 12. Let's just highlight some of the main concepts here. This notes section that I'm going to be working with here, you can find a digital copy under the resources section. We're going to scribble over these notes here, maybe practice a problem or two, but hopefully this will remind you of some of the key things that we learned in each of these sections as you do your review. So. There were 5 main chapters in Chem 12. This first chapter here was on kinetics. We'll pretty much go through 1 unit of review a day. Right? So if you can just pull out this section here, Chemistry 12 summary. This one here was Unit 1. Let's just highlight through some of the main details that we learned in this section. First part, Unit 1 was on reaction kinetics. Kinetics is the whole notion of studying a rate of reaction. If you're asked to define a rate, naturally, we sort of know what rate means, but you cannot use the terminology, oh, it's the rate at which the reaction occurs. You can't define something with the term in it. So if you were trying to define what is a rate here, you can say it's the speed at which reactants, so reactants are on the left side, reactants get used up, so we can say reactants are consumed, or it's the rate at which products are formed. Usually the rates that we're going to do are what are referred to as time rates. So that's why it's going to be something divided by time. Once you identify here what the rate actually depends on, we can actually talk about changing speed. We can make it faster or make it slower. So here lies the first style of question here. They may just say, which of these units here can be used for rate here? Pretty much all we need to do is we actually just want to divide by some unit in time. So if it was something like gram per second, that can be a rate. If it were mole per minute, that can be a rate. It can be liters per hour, right? As long as this bottom unit here is a time value, you can still do it that way. Okay. There was a semester that I actually got people to start typing up a study guide here. You're actually going to see that some of these are actually hyperlinked. If you actually click in the digital copy of the hyperlinks here, it'll actually bring you up to a page where peers from past years, they actually wrote up a little bit. Not every page is complete, but it might be helpful just to click open to the link here. Maybe they have some practice problems for you to do there. Okay. So that's what we mean by reaction kinetics. When we look at the top, what are some features that I can monitor that might change in time that actually give me some evidence or some hint to what the rate actually was? Notice I've already given you a couple. I can measure things like mass change. I can, for example, let's take an open system. An open system, as the name suggests, is entirely open to the environment. An open system, both matter and energy can escape. They can leave. It's problematic if, in the equilibrium section here, if I form a gas, but I'm not talking equilibrium yet. This is something like, let's say I do end up producing a gas. That gas is actually allowed to leave the system. If I put this on a mass balance here and I figure out, well, how quickly does the mass change, I actually know at the rate at which the grams actually starts dropping, that actually is going to be the speed of reaction. If I plotted this out here on a graph, let me just hint to it here. I might be able to plot, let's say, the total mass on the y side. I'm going to plot it against time. Usually reactions are fast at first, so usually the slope is going to be really, really steep at first, and as I steadily consume my reactants, it steadily drops off. Because a rate is supposed to be a change in amount versus change in time, this time it's a change in mass divided by a change in time. While change in mass is just the vertical side, I can just calculate the slope of this curve to actually find the speed. So for an instantaneous slope here, my initial rate here would be the slope of the tangent at t equals 0. Now for slope, I wanted to do y2 minus y1, x minus x1. I needed 2 points. Unfortunately, if I just give you one time, I want to know the speed right at the beginning. I only have one time second here. What you're going to do is draw that tangent. And if you remember here, a tangent is a straight line that essentially follows the curve, so that if I zoom in really, really close, it touches the curve just once. If I zoom in really, really close, I want my red line to actually cover my blue line there. Once you've found your tangent may be different from the person next to you. You just find any 2 points on this tangent here. We do a rise or a run. If I lose this much mass in this time, that's going to give me the rate. That's an instantaneous rate. That's your initial rate. We can also talk an average rate realistically, your reaction started out really fast. You notice that as I steadily lose chemical, the slant here is actually dropping. We can actually calculate what's called an average rate. The average rate just says maybe from start to finish, I just connect the dots. Well, in total, I would have lost this mass. It took this much time for the reaction to complete. If I had a constant slope to get from this point to this point, what is my average slope here? The slope of, we call that line the secant line, is the average rate. So if I just sort of average over, yeah, it was fast at first and then it slows down as you go, if I can just find that constant slope there, that'll still get you to the same point at the same time. Why it was important that I only wanted to have, let's say, one gas that was released. As I get back to a chemical reaction, let's say I have A and B becoming C gas and D aqueous. If I know, hey, my mass here is actually dropping, and I know it's only this one gas that's escaping, I would have the rate expressed in one chemical. Because I have it expressed for C, for argument's sake here, I can use molar mass to get it back to moles. I can re-express it in terms of other quantities as well. I can use a mole ratio. If, hypothetically, both of them are gases, yes, I would end up losing a mass, but I wouldn't be able to track which part was due to C, which part was due to D. I wouldn't be able to do those same mole ratio style questions. Okay, so let me just practice one of those with you here. Let's do a question on the side. Zinc reacts with hydrochloric acid. This produces zinc chloride and hydrogen gas. Hydrogen gas is my only one gas that ends up producing. If I find here, the one gas that gets produced here, if I find I actually produce 5 liters worth of hydrogen per minute, would you be able to re-express it in terms of a concentration per second for HCl? Okay. First thing you want to do is make sure the equation is balanced before we do any stoichiometry. One zinc, I need to have a 2 there. Because I have the rate expressed just for one chemical, I'm ready to do my mole ratio back to get to concentration. So let's just try it out here. Because this one here is a gas, you can assume that it's a STP. I want to express it in terms of a concentration of HCl change per second. Anytime as a fraction, I'm going to write out the fraction explicitly. I produce 5 liters worth of H2 at STP for 1 minute. Because we're a gas at STP, we're going to use 22.7. For the longest time, we've been using 22.4. We slightly redefined standard pressure, so we want to change that to 22.7 now. In terms of mole ratio, for every 1 mole of H2, that's 2 moles of HCl, right? So that's going to be moles there. I would need to actually give you a little bit more information to actually get it to concentration. So let's say my HCl solution was actually 10 milliliters. I can then take moles divided by 0.01000 liters. All the other units would have canceled out. I have moles per liter. That's a concentration HCl. And I also need to get rid of this pesky, well, this is for a whole minute. They just want it per second. So then we just go, well, for every 1 minute, it's also 60 seconds. So that minute there ends up canceling this minute here. Okay? So that's how we convert from one to the other. As we step back over to just recap here, it could track changes in concentration. Now, unfortunate thing about concentration is you actually don't have meters that track every single chemical in terms of concentration. There are particular chemicals. Let's say spectrophotometry here. Spectrophotometry here is able to check the color absorbance or color intensity. We can check acidity using like a pH meter here. That's going to track H+. The one that we did was like copper ions. Copper are actually blue in solution. As you study how things become blue or sort of drop in blue here, that actually is going to track a rate. For reactions that are exo and endo, temperature always refers to a surrounding temperature. We're never microscopic enough to actually feel what the particles are doing. If temperature goes up, how quickly it heats up or how quickly it cools down, that actually tells you the rate of reaction. For pressure and volume, we are specifically looking only at gases. There's an inverse relationship between pressure and volume. Let's say increase in pressure, you can do that by decreasing volume or vice versa. Depending on how you want to set up the system, if I am producing, let's say, one gas, maybe I do want to have a closed system. I just have a pressure sensor. As I end up producing gas in that closed system, the gas is just going to hit the pressure sensor harder. The pressure reading is just going to go up. Or I could have a volume system here. Maybe this is a stretchy balloon. As the one gas gets produced, I end up filling up a balloon size. I can test the volume of the balloon over time. That will also help me track the change. That's how we monitor the rate. I want to track some change divided by some time. Then what we started looking at is, what does this rate here depend on? So what I'm going to do is I'm going to skip down here. Our main concept in this chapter was something called collision theory. Okay. Basically, for a reaction to occur, I need particles to actually collide. The particles have a lot of kinetics to begin with. The first things that end up seeing each other are actually the electrons on one run into the electrons on the other. Like charges repel away from each other. Now, because they were zipping towards each other at such fast speeds, they're not just going to suddenly stop in space, they're just going to gradually slow down. So whenever particles are approaching each other, this happens for successful or unsuccessful, I actually lose kinetic energy. I actually slow down. Because of energy conservation, that energy has to go somewhere. So what I happen to do is I have two sort of bank accounts here. If I transfer money out of the kinetic account here, I actually store money in my potential energy account. There is an energy requirement. There is an energy barrier for the reaction to actually occur. Some bonds need to break, some bonds need to form. The two requirements for a successful collision is one that actually happens. The one that actually ends up converting over to products is one that has enough energy. These particles had to have been speeding towards each other fast enough. They had to trade in enough kinetic to actually overcome the potential energy requirement for them to actually react. That's one requirement. The other requirement is a correct geometry. This is also called favorable orientation, favorable angle of hit. Basically, depending on which bonds are needed to break, which bonds needed to form, there's some sort of energy requirement. So let's just do this on the side here. Let's say I want the reaction between H2 and I2 and ending up forming 2HI. Okay? So maybe one of these was H2, one of these was I2. They have to be on a collision course. If I actually take a look at their geometries here, hydrogen, hydrogen, iodine, iodine, looking at which bonds need to break and which bonds need to form, I actually want hydrogen to be close to this iodine so they can create a new bond. This hydrogen here to be close to the iodine. I would imagine the best geometry for this case here to actually be just sort of straight on like this. What if my hydrogens were sort of unlucky and the hydrogens, they're on a collision course here, hydrogens actually collide with iodine like this? Well, sure, it is going to take some energy requirement to break these bonds. It's going to release off some energy as these new bonds get created. But in this orientation, the hydrogen is close to this iodine, the other hydrogen is not. I'm going to need some extra energy to twist this molecule. That added energy will require a little bit more activation energy. There's just a little bit more energy that you need to put in to break all those bonds to allow the bonds to actually form. Okay? So to sort of study these in a little more detail, we started looking at these potential energy graphs here. These are called PE diagrams, or sometimes also referred to as an enthalpy level diagram. We did start seeing these in Chem 11 as well. In Chem 11, we just cared about start and finish. If I start low and I end high, my delta H, how do you label it? You always just sort of extrapolate the reactant line over. You point an arrow towards the product. If I point upwards, if I go big number minus small number, this delta H here is positive. That means endothermic. An endothermic reaction here has the heat term on the left-hand side because A actually grabs a bunch of heat and then stores it up in becoming B. Right? So that's endothermic. What we learned in this section here was, for this sufficient energy argument here, everything has what's referred to as an activation energy barrier. If I ask you to define activation barrier, you do need to say activation energy, this EA, is the minimum energy. Okay. Now, if you have an infinite amount of energy, of course, you can break any bonds here, no problem. But this is the least that these particles here had to trade in. It's the least. They also want you to have this phrase here, in forming the activated complex. The activated complex is the species here at the top of the hill. Notice that this activated complex here is very, very high in energy. Energy is a bad thing, right? Energy is going to, lots can go wrong when you have energy. So the activated complex here, by definition, it's just when the reactants are touching each other, they're just in the process of rearranging bonds here. So that's what actually makes it very, very temporary, very, very unstable. So what's the activated complex for this reaction? H2 and I2, they've just collided. The activated complex is sort of mid-reaction here. We have the H and the H and the I and the I. Why is it so unstable is I'm just starting to break the H and the I and I bond. So they're no longer holding hands anymore. And I'm just starting to create the H and I, but those bonds haven't fully formed yet. Anything could happen at this point here. Sometimes we use this sort of symbol here, almost like an equal sign and a hash mark. That marking there actually refers to this activated complex here being a transition state. It's just in the process of breaking and forming bonds. That's why it's really, really unstable. So activation energy, we can again extrapolate the reaction line over. I'm going to always point upwards to the top of the hill. This activation energy is the barrier that I need to surmount. It's the amount of kinetic energy that I need to trade in to actually get over this hill here. If I was too slow to begin with, by the time I've actually collided, I've traded as much potential. I've only got up partway up the hill. I wasn't actually able to form the activated complex. I'm actually just going to come back down. And when they're actually leaving each other after colliding, they want to get as far away as quickly as possible. They're going to actually start speeding up. They're going to gain kinetic energy. How did they gain kinetic energy? Is by trading the potential energy back. So that's why they're going to have climbed the potential energy curve on approach. As they leave each other, whether they were successful or not, they're going to actually trade out their potential back for kinetic energy. Okay. So again, emphasis here, the reaction rate depends on this collision theory. We want to look at these two arguments here. Am I doing anything to the energy argument? Am I doing anything to this energy barrier? Or am I doing anything to having more collisions, having a better chance of a correct orientation collision in actually doing this reaction? So as you look through these factors here, I can study these two features. These are totally factors. These ones, like we came back in chapter 2, they were things that I can actually poke at the system with. This factor here, I still need to tell you whether I increase this or decrease this. So for example, in terms of a temperature change, when I increase the temperature, the particles generally get faster. The reaction time decreases. There's always an opposite relationship between time and rate. Remember, rate was a divide by time. As the denominator gets smaller, the rate itself will increase. So in general, if you heat things up, the rate gets faster. Which of these features, sufficient energy or correct geometry, did I actually influence? Now, at this point here, we did a kinetic energy distribution. The kinetic energy distribution, although we would typically draw it number and then kinetic energy like this, what they've done is they just sort of rotate it 90 degrees. So number is actually here, the kinetic energy. Kinetic energy is your sort of moving energy. So this is actually plotting for you the speed of the box. Inside the container, you may have some average temperature. The average temperature here is a measure of the average kinetic energy. Most of the particles have some moderate amount of energy. At any given time, though, although most of them are moving at a medium speed, you're always going to have some that are fast and some that are really, really slow. So we have less number of them that are slow, less numbers of them that are really, really fast. Because of this sufficient energy argument, because there is this energy barrier that I need to surmount to actually get over the hill, there is some energy requirement. Only the particles that were actually moving fast enough can actually react. So again, they rotate 90 degrees here. So this one here, that's the energy barrier. That's the minimum that you need to end up forming the activated complex. It's only the particles that are more than that are the really fast ones that can actually get over this hill, that can actually start breaking bonds and end up forming bonds. What we do when we increase the temperature is we actually heat up the entire box. What ends up happening is this curve here ends up shifting over. We're going to end up having the activation barrier actually stays constant. The requirement that you need to actually for the reaction to occur actually stays constant. But what we've done is we've actually made it so that we have more particles that have enough energy to actually overcome the hill. Let's just write this down here. For increased temperature here, we actually have more particles with sufficient energy, with enough energy to overcome the activation barrier, to overcome the energy requirement. Okay? Activation barrier, the requirement didn't change. We just happen to have more particles that can do it. Second property here we have is concentration. Again, that's a factor. If I increase the concentration, generally the reaction rate increases. Now, increasing this concentration here means I just toss in more particles. As I toss in more particles, nothing's happened to the energy. My curve here may have just sort of increased like this, right? Nothing really has changed. It's just sort of by proportion here. But what I've done here is, even though the energy barrier hasn't changed here, I've changed this sort of correct geometry argument. I'm going to actually have increased the number of collisions. The more collisions that I have, now many times you're going to have millions and millions of collisions. I'd say 95% of them would be unsuccessful anyways. If you have more collisions, you don't just leave it like that. You're going to actually have a better chance of good geometry. If one collision happens and it's not really at the right angles, don't worry, they're going to collide again, and maybe that collision will be better. So anything that you can do to increase the number of collisions, to increase the chances for having a good geometry collision, that should increase the rate. If you have nothing else to go on, there's a certain order of rates. So as a solid, the particles are just really tightly packed, really slow. Aqueous solutions, aqueous in the sort of liquidy state, in the dissolved state, they're just slipping and sliding. They're in close contact, lots of collisions. Aqueous has the benefit that things are charged as well. Those charges, opposite charges attracting, may actually control the geometry as well. Maybe positive runs into negative, and that actually allows the right particles to collide. Again, better chance of good geometry, the faster the reaction is going to be. They always like asking this here, which of these factors only affects a heterogeneous reaction? Hetero means the reactants are actually in different states. That's when we're going to actually have a surface. So if you imagine with me here, I'm just going to draw it on the side. Let's imagine I start off with a solid. You're going to use the terminology here, a chunk of solid. So it's an entire material here. We're going to have an aqueous. This one here is heterogeneous. The rate only depends on the reactants. So let me just make up some of this here. So A becomes 2B. This can become solids later on. I don't really care. Okay, the rate only depends on the reactants colliding. Okay, so the rate depends on reactants only. All right. In terms of having collisions, because we are sort of hidden away where this chunk of material, this solid here, the collisions are only going to happen on the outermost coating. There's actually a lot of inside particles that actually don't see the outer coating. What you can do then is you can actually powder this chunk, take the same amount, but actually make it a powder. In powder, all we've done is we've actually increased the number of particles that are available for collision. As these particles here end up colliding with the powder, we have more collisions, again, better chance of a good collision, and therefore a faster reaction rate. So surface area does sort of work its way out to a concentration argument. Similarly for pressure and volume, I always think of pressure and volume as opposites. So let's start off with a big container, and let's end up squeezing the container into a really tiny container. Instead of, let's say, I having 5 particles in a big container, now I have 5 particles in a small container. Again, they're in much closer contact because there's going to be more contact, there's going to be more collisions. More collisions means better chance of good collisions, good geometry, and that's why it's going to be faster as well. There is one they're sort of including. Sometimes they just give you a statement. Hey, gold is really unreactive. Why? We saw on our electrochem table, gold is actually really bad at oxidizing. There's many things that oxidize before it, but it's just natural to gold. Something chemically speaking is making it unreactive. It's not because it has low surface area. It's not because we are at too low temperatures or whatever. We're just going to quote that generally as a nature of reactants. It's just the way the chemical is. So NOR. It has to do with maybe the bond strength. Maybe the chemical itself holds itself together really well. Maybe there's a lot of bonds. It's a really high energy required to break it apart. If you have nothing else to go on, you can say nature of reactants. The one last feature that we talked about here was a catalyst. A catalyst is a chemical that you add to the system that always speeds up reactions. If you want the opposite, you add something and it decreases the rate here, we actually refer to it as an inhibitor. How does a catalyst work? A catalyst actually provides an alternate mechanism. A mechanism is how the reaction actually proceeds. It's the actual step-by-step sequence and what ends up happening. If the catalyst provides an easier mechanism, that easier mechanism has a lower activation barrier. So let's just do it on this curve down here. Right now here we already have an exothermic reaction. It should be spontaneous. It should want to go forwards. Maybe my activation barrier happens to be too high. This energy requirement here is too much. I don't have fast moving particles enough to actually get over this hill. By adding a catalyst, we actually are able to take a detour to get from reactions to products, but the detour may be taking many steps. Those many steps here, you'll notice the energy barrier here is actually a little bit lower, right? So that means my particles might very well be the same speed as they were before, but the energy requirement for them to break bonds here is actually less, so therefore it's actually easier to react, therefore it's a faster reaction. Okay. This actually gave rise to reactions being reversible. So if I want to go forwards, forward reactions is reactants become products, that's left to right. The reverse reaction, while I could technically surmount these hills and go in the reverse direction, products could also, going right to left, go in the reverse direction. Okay, So that's what a catalyst does here. An inhibitor, very similarly, would accidentally provide a reaction rate that's even higher, would actually stop some of these particles that were going to react, and it actually is going to make the reaction harder. So on the back side here, we finished off with some mechanism work. A mechanism, again, is the actual sequence of steps, is the actual ordering of which happens first, which happens afterwards to make up the overall equation. Let's say this is the mechanism. So this one here is going to be step 1, step 2, step 3. They're not going to ask you to propose a mechanism from scratch. At best, they can give you this, and they can ask you, well, what's the net reaction? What's the overall reaction? In some sense, all you need to do is you need to just put all the left-hand side on the left, all the right-hand side on the right. It's just that there may be some chemicals that actually cancel out. For example, step 1 creates ClOH. Step 2 has ClOH go in. That cancels out. There's no point writing it on both sides. We have an IOH. IOH got created on step 2, gets used up in step 3. That also doesn't appear overall. The hydroxide that got created on step 1 also gets used up in step 3. It doesn't have to be successive steps. It doesn't have to be used up immediately afterwards. But if by the end of it, it still gets used up, we call those chemicals there, we call these ones here an intermediate. They are produced early, and they're ending up being used up. In this case here, we also see water. Well, water's on the left side, water's on the right side. That also cancels out. Water actually doesn't participate in the overall equation. But wait, water wasn't created first and used up later. If I actually put it in first and I actually get it out later, we actually refer to it as a catalyst. So water in this case here is actually a catalyst. It also gets consumed. It also gets canceled out before the overall equation. For the catalyst, we usually put the catalyst above the arrow to tell you that is present in the reaction. Being a 3-step mechanism here, all 3 steps are going to have an activation barrier. Let's just use H. Let's use a reaction coordinate here. Every step is a reaction in itself. Every step has an activation barrier. There is going to be one step that's going to be slower than the other 2. This step is going to be called the rate determining step, or RDS. This is the one that's the slowest because it actually has the highest activation barrier. So I have a 3-step pathway. Maybe the first one here was relatively easy. The second one, whoa, really, really high. Then the third one, relatively easy. They always like asking this question here. As you add a catalyst and as you start making the reaction easier or whatnot, what doesn't change? The delta H doesn't change. The catalyst still gets you from the same start to the same finish. If I sort of extrapolate that line over, the delta H actually doesn't change. It's actually the energy barrier that was shrunk here. In this case here, my step number 2 had the biggest energy barrier, right? That's why that's the slowest step here. If you were to invest in speeding any of these reactions up, I would speed up the second reaction. Step 1 and step 3 practically happen in a split second like that. This one here allows for the possibility of 3-particle collisions, 5-particle collisions, because otherwise it's really hard to get, let's say, even 3 particles. It's really hard for them to hit the same spot in space. They need to come in, A, B, and C have to collide together. They have to have the right energy, right geometry. It's sort of stacked against it. It probably wouldn't occur. Okay, so I have another look over this section here. Let me know if you have any questions. Thanks, guys.